Time dilation describes the phenomenon where time passes differently for observers in relative motion. Time dilation also occurs at varying gravitational potentials, as predicted by Einstein's theory of relativity. Time dilation is a consequence of Einstein's theory of relativity. Special relativity describes time dilation effects arising from relative motion. As an object's speed increases, time slows down for that object relative to a stationary observer. Time dilation is a consequence of the constant speed of light for all observers. General relativity explains time dilation as a consequence of gravity. The stronger the gravitational field, the slower time passes relative to regions with weaker gravity. Time dilation is a relative effect, dependent on the observer's position within a gravitational field. As an object's velocity approaches the speed of light, time slows down significantly for that object relative to a stationary observer. At 99.9999%, the speed of light, one day for a space traveler equates to decades passing on Earth. The dramatic time dilation effect is a direct consequence of approaching the universal speed limit. Near light speed travel enables a form of one-way time travel. Travelers experience less time passing compared to those who remain stationary. The faster the speed, the greater the difference in experienced time. Time slows down in stronger gravitational fields. Massive objects warp space-time. The warping of space-time causes time to pass more slowly near massive objects. Near a black hole, time slows down significantly relative to Earth due to intense gravitational forces. An hour near a black hole can be equivalent to years on Earth due to the effects of time dilation. Extreme gravitational forces around a black hole cause significant time dilation. Approaching the event horizon of a black hole causes significant time dilation. An observer near the event horizon would perceive the universe aging at an accelerated rate. Time progresses minimally for an object hovering near a black hole's event horizon relative to the rest of the universe. Time dilation, a concept predicted by relativity, was experimentally verified using atomic clocks. Atomic clocks flown on high-speed jets experience time at a slower rate compared to stationary clocks on Earth. The experiment confirmed that relative motion affects the passage of time, validating the principles of special relativity. GPS satellites experience time dilation due to their orbital speed. Time dilation also occurs due to the satellite's distance from Earth's gravity. Engineers must correct for time dilation effects to ensure accurate GPS positioning. The Pound-Rebka experiment verified that gravity influences the passage of time. The experiment involved measuring gamma rays emitted at different altitudes to detect gravitational redshift. Gravitational redshift confirms that time passes more slowly in stronger gravitational fields. Time dilation is a real and measurable phenomenon. Time dilation constantly occurs around us due to variations in gravitational potential and relative velocity. Experiments confirm the existence of time dilation. Orbiting a supermassive black hole for an hour can cause significant time dilation. Due to extreme gravitational effects, time passes much slower near a black hole relative to distant observers. Returning to Earth after orbiting a black hole could result in centuries having passed on Earth. From the traveler's perspective, the universe's time appears to have accelerated. The traveler's personal timeline remains unchanged, experiencing time at a normal pace. The perceived time dilation is due to the relative motion between the traveler and the rest of the universe. Time is relative. Its passage varies for different observers. An observer's motion affects their experience of time. Gravitational environment also influences the flow of time. Time dilation has significant implications for future space travel. The effects of time dilation become more pronounced as speeds approach the speed of light. Space missions approaching light speed will experience substantial differences in elapsed time compared to Earth. Interstellar travel at near light speed results in significant time dilation. Returning to Earth after interstellar travel means encountering a future thousands of years advanced. The temporal disparity between space travelers and Earth creates emotional and social challenges. Long-duration space missions must account for time dilation effects. Astronauts on the ISS age slightly slower than individuals on Earth due to relativistic effects. Even at the speeds of the ISS, time dilation is a measurable phenomenon. Precise atomic clocks are utilized to compare time flow variations at different altitudes on Earth. These comparisons serve as continuous tests of relativity theory. Atomic clocks provide the accuracy necessary to detect minute time differences predicted by relativity. GPS satellites provide daily tests of relativity through precise time measurements. Spacecraft timing systems offer another method for validating relativity in extreme conditions. High-altitude experiments contribute to relativity testing by measuring gravitational effects on time. Time may soon be utilized as a tool for various applications. Long-distance travel could potentially leverage time as a medium. Time-based technologies could enhance long-distance communication capabilities. Time dilation challenges the concept of a universal present moment. The relativity of simultaneity arises from the variable nature of time. Time's elasticity implies that simultaneity is not absolute, but depends on relative motion. The warping of time raises fundamental questions about the nature of aging. The perception of time's passage challenges the notion of a fixed, linear path. Time's malleable nature suggests it may be a landscape that can be shaped and influenced. If time is not absolute, each moment may contain infinite possibilities. The observer's location and experience can influence the perception of time and reality. Multiple realities can exist simultaneously, contingent on individual perspectives. Time dilation describes how time is affected by relative motion or gravity. Increased speed causes time to slow down relative to a stationary observer. Stronger gravitational fields also cause time to slow down. Deep space exploration involves traversing vast physical distances. Navigating deep space also means confronting the mysteries of time. The challenges of deep space exploration extend beyond physical travel to include temporal considerations. Space missions expand our comprehension of life, aging, and return processes. Time behaves differently in space, affecting the aging process. Understanding these differences is crucial for long-duration space travel. In the vastness of space, time's conventional constraints are challenged. The universe invites a reconsideration of fundamental concepts of reality. Space presents an environment where standard temporal rules do not apply. Special relativity posits that the laws of physics are consistent for all observers in uniform motion. The speed of light in a vacuum is constant for all observers, irrespective of the motion of the light source. These two principles form the foundation of special relativity. The Lorentz transformation mathematically describes coordinate transformations between inertial frames of reference. It accounts for the effects of special relativity on measurements of space and time. The Lorentz transformation ensures that the speed of light remains constant in all inertial frames. The time dilation equation, T equals T sqrt 1v2c2, describes the relationship between time passage for moving and stationary observers. In this equation, T represents the time experienced by the moving observer, while T represents the time experienced by the stationary observer. The variables v and c represent the relative velocity between observers and the speed of light, respectively. Length contraction is a consequence of special relativity. An object moving at high speed appears shorter in the direction of motion. Length contraction is observed by a stationary observer. As an object's speed increases, its relativistic mass also increases. Relativistic mass approaches infinity as an object nears the speed of light. It is impossible for an object with mass to reach the speed of light due to the infinite energy required. General relativity describes gravity as the curvature of spacetime. Mass and energy cause the curvature of spacetime. The curvature of spacetime affects the motion of objects and the flow of time. Einstein's field equations mathematically link the curvature of spacetime to the distribution of mass and energy. These equations provide a framework for understanding gravitational phenomena. The curvature of spacetime is directly proportional to the mass and energy density. Gravitational lensing occurs when the gravity of a massive object bends the path of light. This bending of light distorts and magnifies the image of the distant source. The gravity of a massive object acts as a lens, focusing light from a source behind it. Gravitational redshift occurs when light loses energy escaping a gravitational field. As light loses energy, its wavelength increases, shifting towards the red end of the spectrum. The The change in wavelength is a direct result of the light's interaction with the gravitational field. Black holes are formed by the gravitational collapse of massive stars. The collapse results in a singularity, a point of infinite density and curvature in spacetime. At the singularity, the laws of physics as we know them break down. The event horizon of a black hole defines the boundary beyond which escape is impossible. Not even light can escape the gravitational pull beyond the event horizon. The event horizon effectively defines the surface of a black hole. The singularity at the center of a black hole is a point of infinite density. The singularity possesses zero volume. At the singularity, the known laws of physics break down. Frame dragging, also known as the Lentz-Thirring effect, occurs when a rotating massive object drags space-time around it. This effect is a consequence of general relativity, where gravity is described as the curvature of space-time. The magnitude of frame dragging depends on the mass and rotation speed of the object. Gravitational waves are disturbances in the curvature of space-time. These waves are caused by accelerating massive objects. Merging black holes and neutron stars are major sources of gravitational waves. The detection of gravitational waves by LIGO and Virgo provides direct evidence for Einstein's theory of general relativity. Gravitational wave detection opens new avenues for astronomical observation. Complementing traditional electromagnetic methods, LIGO and Virgo act as large-scale interferometers detecting minute changes in spacetime caused by passing gravitational waves. The twin paradox is a thought experiment exploring time dilation in special relativity. One twin travels at high speed relative to the other, who remains on Earth. Upon reunion, the traveling twin ages less than the twin who remained on Earth due to time dilation. The twin paradox is resolved by the traveling twin experiencing acceleration during the journey. Acceleration breaks the symmetry between the frames of reference of the two twins. The traveling twin's acceleration leads to a difference in aging compared to the stationary twin. The Hafele-Keating experiment confirmed time dilation using atomic clocks flown on commercial airplanes. Atomic clocks on airplanes were compared to a stationary clock to measure time differences. The experiment demonstrated that time is relative and affected by motion, as predicted by Einstein's theory of relativity. Muon decay demonstrates time dilation, a consequence of special relativity. Muons, created in the upper atmosphere, have a short lifespan. Due to time dilation, muons reach the Earth's surface despite their short lifespan. GPS satellites require time dilation corrections rooted in both special and general relativity. Special relativistic time dilation arises due to the satellite's high orbital velocity. General relativistic time dilation is caused by the satellite's weaker gravitational field compared to Earth's surface. Atomic clocks achieve high accuracy by using the resonant frequencies of atoms to measure time. These devices are extremely precise timekeeping instruments. Atomic clocks are used in various applications requiring precise timing. Atomic clocks are essential components in global positioning systems, GPS. Atomic clocks ensure precise time synchronization in telecommunications networks. Atomic clocks are utilized in fundamental physics research to test the constancy of physical laws. Time transfer techniques enable precise synchronization of clocks at different locations. These techniques are crucial for testing theories of relativity. Precise clock synchronization facilitates various scientific experiments. Very long baseline interferometry, VLBI, employs multiple radio telescopes to observe a single astronomical object. This technique achieves high angular resolution, significantly enhancing observational precision. VLBI enables precise measurements of both time and space, contributing to a deeper understanding of the universe. Space-time coordinates describe events in 4 dimensions. These coordinates provide a framework for understanding relativity. Space-time combines 3 spatial dimensions with 1 time dimension. Minkowski space is a mathematical model that combines space and time into a single 4-dimensional continuum. In Minkowski space, space and time are treated as interconnected dimensions rather than separate entities. Minkowski space serves as the mathematical foundation for special relativity. Geodesics represent the shortest paths between 2 points in spacetime. These paths illustrate the trajectories of objects moving under the influence of gravity. Gravity dictates that objects follow geodesic paths, minimizing distance through curved spacetime. World lines represent the paths of objects through spacetime. These paths illustrate the history and motion of objects. World lines visually map an object's trajectory across both space and time. Light cones illustrate the potential trajectories of light rays originating from a specific event in spacetime. These cones define the causal structure of the universe by showing which events can be causally connected. The boundaries of the light cones represent the maximum speed at which information can travel. Causality dictates that a cause must always precede its effect. Information cannot travel faster than the speed of light, upholding causality. Causality is a fundamental principle governing the sequence of events in the universe. Closed time-like curves are hypothetical paths through spacetime. These curves theoretically allow for the possibility of time travel. Time travel via closed time-like curves could potentially lead to paradoxes. The grandfather paradox is a theoretical contradiction arising from time travel. This paradox involves a time traveler preventing their own birth by altering the past. The grandfather paradox highlights logical inconsistencies inherent in backward time travel scenarios. The self-consistency principle posits that time travel is permissible only if it avoids paradoxes. Time travel must unfold in a manner that maintains a consistent timeline. Paradoxes are avoided by ensuring events remain logically consistent within the timeline. The multiverse interpretation proposes that time travel can lead to the creation of new branching timelines. These branching timelines diverge into alternate realities, each with its own unique history and future. Diverting to alternate realities avoids paradoxes that might arise from altering the past in a single timeline. Wormholes are theoretical tunnels through space-time. These tunnels could connect distant regions of the universe. Wormholes may potentially allow faster-than-light travel or time travel. Exotic matter is a hypothetical substance characterized by negative mass-energy density. The existence of exotic matter could potentially stabilize wormholes. Stable wormholes created by exotic matter might allow for traversable time travel. Quantum entanglement is a phenomenon where two particles become correlated. Entangled particles maintain their correlation regardless of the distance separating them. Quantum entanglement has the potential to enable faster-than-light communication. Quantum tunneling allows particles to pass through potential barriers despite lacking the classical energy to overcome them. This phenomenon defies classical physics, where particles are expected to be reflected by energy barriers they cannot surmount. Quantum tunneling is a fundamental concept in quantum mechanics, with implications in various fields, including nuclear fusion and semiconductor technology. The Heisenberg uncertainty principle establishes a fundamental limit on the precision of simultaneously knowing certain pairs of physical properties. Position and momentum are a key pair of physical properties affected by the Heisenberg uncertainty principle. Increasing the accuracy of one measurement inherently decreases the accuracy of the other. The information paradox emerges from the apparent disappearance of information as matter enters a black hole. This loss of information seemingly contradicts the fundamental principle of quantum mechanics, which states that information cannot be destroyed. The paradox challenges our understanding of both black holes and the laws of quantum mechanics. The holographic principle proposes that the information within a volume of space can be represented on its boundary. This principle suggests an encoding of information similar to a hologram. The information contained within the volume is fully captured on the two-dimensional boundary. String theory replaces point-like particles with one-dimensional strings. These strings are theorized to be the fundamental building blocks of all matter and forces in the universe. String theory aims to unify all fundamental forces and particles into a single theoretical framework. Loop quantum gravity is a theoretical framework that quantizes space-time. This quantization replaces the smooth space-time continuum with a discrete structure of loops. The fundamental concept involves representing space-time as a network of finite loops at the Planck scale. Dark matter is a hypothetical form of matter that does not interact with light. Although dark matter does not interact with light, its gravitational effects are observable. The presence of dark matter is inferred through its gravitational influence on visible matter. Dark energy is a hypothetical form of energy. Dark energy is causing the expansion of the universe to accelerate. The exact nature of dark energy remains unknown. The cosmological constant represents the energy density of empty space. This energy density contributes to the accelerated expansion of the universe. The cosmological constant is a term in Einstein's field equations. Future research will explore the mysteries of time, space, and the universe. Cosmology aims to push the boundaries of our understanding of the universe. Physics will continue to investigate fundamental laws governing the cosmos.